Hello, in this video we're going to take a look at some very simple principles relating to the normal function of the basal ganglia and cerebellum. Now this is traditionally a very complex area causing a lot of trouble for students, and what I'm really trying to do is simplify this as much as is possible in order to highlight the important overarching concepts. So what we're going to do is we're going to look at how the basal ganglia and cerebellum work, and we're going to do this together. So we're going to look at the similarities between the systems involving basal ganglia and cerebellum. So the first thing that I want to do is I just want to separate the page into two halves, and the top half we're going to consider the basal ganglia, and the bottom half we're going to consider the cerebellum. So basal ganglia on the top and cerebellum below. And as I said, we're going to look at the commonalities between the two systems. Now, let's start off with the basal ganglia, and the first thing that we're going to do is just draw on something fundamental that we're all quite happy with, well, we should be by now, and that is the fact that the primary motor cortex, which I'm going to abbreviate as M1, communicates with lower motor neurons via the corticospinal tract. Okay, so this is the corticospinal tract here. So therefore, this line represents the axons of upper motor neurons originating in the primary motor cortex and heading down through the cord to lower motor neurons. And of course, lower motor neurons are the neurons which are responsible for creating behaviour. And in fact, by physiologists such as Charles Sherrington, these lower motor neurons are known as the final common path. So these create behaviour because they communicate directly with muscle. Now, the problem that we have is that if this was the only system that we had in place, actually we would find that the movements mediated purely by the primary motor cortex and its communication with lower motor neurons might not get us to our goals very efficiently, because the motor plan created by the primary motor cortex is imperfect. Okay, so we can think of this motor plan created by the primary motor cortex as imperfect and not necessarily the ideal way for us to achieve our goals. So what the motor cortex needs to do is, if you like, it needs an editor. It needs another part of the brain to take a look at the plan that it has created in order to achieve a goal and edit it, so to maybe remove inappropriate movements or add in more appropriate movements, or at least to facilitate more appropriate movements. Now, to highlight that, what we should do is think about a common behaviour that we all do, and let's think about picking up a cup. So I'm going to draw here just a very, very simple depiction of a person. So here is the trunk, okay? Here is the shoulder joint, here is the arm, here's the elbow joint, here are the digits with the wrist joint just there. And if we wish to pick up a cup, which I'm going to depict here, I'm no Da Vinci, but it still gets the message across. If we wish to pick up a cup, then we need to do a certain number of things, and we need to coordinate the activity of our muscles appropriately. So the first thing to realise is that for every one of the joints that I've highlighted, there is a set of agonist and antagonist muscles at play. So, of course, with respect to muscles acting on the wrist and the digits, we have agonistic muscles that will flex, and it is flexion of the fingers that we want, isn't it, to pick up this cup, as opposed to extension of the fingers that would be mediated by these muscles. If we wish to bring the cup to our mouths, we need flexion of the elbow, as opposed to extension of the elbow. And if we wish to bring the cup even closer to our mouths, we need flexion of the shoulder as opposed to extension of the shoulder. So what I've tried to show here is that in order to carry out this behaviour, that is, in order to drink from a cup, we need to flex, flex and flex at the wrist, elbow and shoulder. We do not want to be doing extension because that would not bring the cup to our mouths and would not lead to us being able to take a drink. So what needs to happen is that the crude motor plan produced by the primary motor cortex needs to be analysed, and those components of the plan which lead to flexion in the joints need to be facilitated, and those components of the plan that might lead to inappropriate extension of the joints need to be inhibited or edited out. So let's try and depict that in our diagram here. So the primary motor cortex actually sends this motor plan down to the basal ganglia. Okay, and I'm treating the basal ganglia in their entirety here. I am not separating the basal ganglia out into striatum, lentiform nucleus, etc. We're just treating the basal ganglia as a whole. So the primary motor cortex sends its motor plan, if you like, down to the basal ganglia, and the basal ganglia take a look at the plan and edit it. All right, and the way that they edit it is like this. If, upon analysing the motor plan, the basal ganglia detect movements which are appropriate, so in this case those movements of flexion, then they will facilitate the primary motor cortex, and they facilitate the primary motor cortex via a pathway known as the direct pathway. Whilst if the basal ganglia detect movements in the plan which are inappropriate, and in this case that would be extension, they will inhibit these inappropriate movements. And this inhibition of inappropriate movements is carried out by the indirect pathway. So what we have here is a loop, and this loop is able to analyse our motor plan from the primary motor cortex and refine that plan such that the instruction that is sent to the lower motor neurons via the corticospinal tract is most likely to lead to the performance of our goal. So this is the simple principle behind the normal functioning of the basal ganglia. That is that the direct pathway facilitates appropriate behaviours, whilst the indirect pathway inhibits inappropriate behaviours. Now we can of course add further detail to this if we wish. For example, recall that if you wish to speak to any part of the cerebral cortex, including the primary motor cortex, you actually have to go through the thalamus. So this arrow here is not a direct connection. Actually, this is there is the thalamus just interposed at this point, acting as the gateway between the basal ganglia and the primary motor cortex. And that applies to both pathways. But that doesn't affect the principle. The principle remains that the basal ganglia are acting, if you like, as editors of the motor plan produced by the primary motor cortex. So now let's think about the role that the cerebellum has to play and how the normal function of the cerebellum ties in with the normal function of the basal ganglia. And we're going to take exactly the same approach. So the primary motor cortex communicates with lower motor neurons via the corticospinal tract, and it is the activity of lower motor neurons and their influence on skeletal muscles that leads to behaviour. And just like in the case of the basal ganglia, the cerebellum receives input from the motor cortex concerning the motor plan. So here is the cerebellum. Okay, so we have the beginnings of another one of these loops. So the cerebellum is looking at a slightly different aspect to the motor plan than the basal ganglia. Recall that the basal ganglia is looking at this and deciding whether movements are appropriate or not to achieve a goal. What the cerebellum is doing is looking at the sequence of movements and deciding whether this is the most important whether this is the most appropriate sequence of movements to perform our goal. So let's think about how we can relate that to our little drawing above. So once again, our person here is picking up a cup. And we said, didn't we, that in order to pick up the cup, we need flexion of the fingers, flexion of the elbow, flexion of the shoulder, and that extension would have been inappropriate in this case. However, there is a sequencing as well that needs to be carried out. For example, in picking up the cup, it would be inappropriate to flex the shoulder first, then the elbow, then the wrist and fingers. It would be most appropriate to flex the fingers first, then the elbow, and then the shoulder. So it is important that we get the sequence right, in addition to ensuring that the most appropriate movements are selected. And that is the role of the cerebellum. Now, the more astute amongst you might have realised that, of course, the position of the limb may vary, and therefore the most appropriate sequence of movements might be different in order to achieve the same goal. So picking up a cup from a low table or the floor might need a very different sequence of movements compared with picking up a cup from a high shelf. So what the cerebellum needs to receive is not only information from the primary motor cortex concerning the motor plan, but also information from the sensory system. And it receives this information from two sources. It receives this information from the primary sensory cortex, which I'm abbreviating as S1, and it also receives this information from the spinal cord, from proprioceptors in the muscles via the spinocerebellar tract. Okay, so the spinocerebellar tracts carry proprioceptive information up through the spinal cord to the cerebellum itself. So the cerebellum is getting information concerning the motor plan from the primary motor cortex, and it is using that in conjunction with information from the sensory cortex and the spinocerebellar pathways in order to establish what the most appropriate sequence of movements should be. The cerebellum then communicates back with the primary motor cortex, and once again, like in the basal ganglia, this would be via the thalamus, although we are not showing that. So once again, we have a loop whereby the cerebellum is analysing this motor plan from the motor cortex and integrating that with information from the sensory systems in order to come up with the most appropriate sequence of muscle contractions to carry out our ultimate behaviour. And really, that is all that there is to it. Now, obviously, I've missed out a lot of detail. And obviously this is not a highly detailed neurophysiological treatment of these systems. However, what I hope is that this will give you some idea of the basic driving principles behind these loops between the motor cortex and basal ganglia or cerebellum, and give you some idea of how the pathological consequences of damage to these structures might manifest. So thank you for listening.